In this one, we have a quarter circle of charge, it looks like. Positive charge uniformly distributed over a quarter circle of radius r, as shown in the picture. Points A and B and C are located as shown, with A and C located symmetrically relative to the x-axis. Express all algebraic terms in terms of the given quantities and fundamental constants. So possible. So rank the magnitude of the electric potential at points A, B, and C from greatest to least, with number one being greatest and number one being greatest. If 2 points have the same potential, give them the same ranking. From greatest to least, with number one being greatest. So the highest electric potential will be at B. So that's the highest electric potential. A and C will be the same, but will be less. So it's just proximity. So because B is closer to the arc than A and C, that's why. And you have to give reasonable justification, but you do have to indicate that because A and C are symmetrically located the same distance away from the arc, that's why they would have the same electric potential. If you didn't say that specifically, you could have lost a point. Any question about this one? All right. I assume that wasn't your question then? So moving on to the next part, part B. Determine an expression for the electric potential at point P due to the charge Q. So if you're keeping notes about what I think you should be knowing about the difference between electric potential and electric field, one of the notes you should keep is that we calculated the electric potential originally for a point charge by looking at the amount of energy required to go from infinity to a location in space against or with an electric field. It's important to understand that we started from a position where there was no electric field measurable from the charge distribution. And we had to travel to a location, in this case, point P, from infinity. And that's where this function comes from. Now, in this problem, we can use this holistically, meaning we can just use this as a direct application to what the electric potential must be at point P, with each portion contributing to the amount of electric potential, not the direction, because potential doesn't have direction. However, if you were to be doing any problem that involves a conductor or a conducting shield or something where you had to go through, say, they could have just as easily said there is a metal box exists in space, in front of our object. Well, you'd have to be more careful then. You'd have to find the electric potential to this point from infinity and then recognize that there's no change in potential to go across to getting to this point. Now, for a problem like this, they couldn't ask that because the contribution would be too hard to calculate. But you have to remember that electric fields are kind of from the inside out, while electric potentials are from the outside in. And it's just a good thing to kind of get into your head. So we can use this, but you need to be careful about how it's used. It is relative to a point at infinity. And that has to be the basis for how it is used. So I'm going to use it, and I'm also going to take a huge amount of shortcuts in using it. In fact, I'm not going to do any integration. We know how much charge there is total, and we know how far away each individual piece is from point P. So because there's no directional component, the electric potential has to be just QK over R. And that's it. And I don't know that you had to show hardly any work for it to get any of the points. It does say determine, not derive. So I think any indication that you would, maybe write that every point is equidistant from point P, every point of charge is equidistant from point P. I don't know how much you'd have to say, but I bet it's only worth 1 point anyways. I can't imagine it's worth more than that. But I'm not looking at the solution set. Any follow-up? All right. C, a positive point charge Q with a mass M is placed at point P. All right, a positive charge Q is placed at point P. It has mass m. Derive an expression for the speed of the point charge when it is very far from the origin. Derive suggests we have to use at least some kind of first principle. I'm not going to use a first principle, but I am going to use two principles: the definition of electric potential and conservation of energy. Right now, we know that there's a certain amount of energy associated with this system because the charge was placed at point P. The amount of energy in the system is Q times the potential. So now that I know how much energy is in the system, assuming that by saying very far away, we were talking about getting to a point where all this potential energy has been converted to kinetic energy, I'm going to say QV equals 1/2 mv squared. And this is how you will find the velocity at a distance that is very far away from the line of charge, or from the arc of charge. Good enough? All right, m is going to be in your answer. That should be obvious because it's got inertia. On the dot representing point P, indicate the direction of the electric field at point B due to charge Q. We have a symmetrical charge distribution, which means although the piece that I've circled contributes to an electric field in this direction, I have an equal and opposite piece located on the bottom, so that I'm going to have a total electric field that has no y components and only x components. So I expect that my electric field will be in this direction, horizontally along x. So you're probably getting 1 point for that too. Derive an expression for the magnitude of the electric field at point P. Now we have something. First, the word derive is there. So again, we have to start with a first principle. And I think the first principle is going to be the expression for the electric field. None of the information that I have here is going to serve me, so I'll get rid of all of it. I'm going to do a couple of things here, but I do want to point out, I don't know that I would have to do all of the steps I'm about to do, because there is a certain amount of symmetry here that I could use, but I'm going to be thorough. So first, I'm going to identify a piece of charge somewhere along this run, and I'm going to say my piece is right here, and I'm going to call it dq. I'm going to say that this piece of charge contributes to an electric field dE that is equal to k dq over r squared in the r hat direction. And that piece of electric field will contribute to that piece of charge will contribute to a piece of electric field that would be something like that. And maybe not perfectly in line. Maybe Mr. Shelton could do better. Maybe not. He's not particularly good at his job. He'll do better. He'll try. At least he's not being shockingly condescending right now. But maybe I do need to go back to, what they say, elementary school, to learn how to spell so I don't sound like an idiot. So the internet's not a nice place, apparently. So well, it's okay. I'd say I'm thick-skinned. I am not, because I clearly keep bringing it up. So not particularly thick-skinned. The next step after I identify my piece of charge is to try and find a way to point to that piece of charge and use a system that could easily identify both the first piece of charge and the last piece of charge. I'm going to point to that piece of charge by first indicating that it begins here at that point, and that point can be addressed by a radius and an angle. So I'm going to address each piece by using the radius and an angle, and I'm going to say the size of that piece is a piece of arc length, and that the arc length is related to these two values, in that the amount of arc length there is r d theta. And then I'm going to represent Q in terms of these by using the charge density, lambda, to say that dq is equal to lambda ds. And so this is how I'm identifying the size of the piece of charge. It clearly articulates the letters that I'm going to use to indicate where each piece is. Obviously, I'm going to have theta go from either negative beginning of rod to positive beginning of rod, or go from 0 to one direction and then double the contribution. I'm likely to do it that way. We've talked about this before, but I just need to make sure that my system can address every piece of the rod, and I think R theta can address every piece of the rod. I do want to take a moment and realize I don't have an expression for lambda that's in terms of the variables that are allowed. I will need to come up with an expression for lambda, which has to be the charge divided by the length of the rod. They tell me it's a quarter of a circle. So since a full circle is 2 pi r, a quarter of the circle will be 1/2 pi r. That would be the appropriate length. So I'm going to say that my lambda is total charge divided by total length, which is pi r over 2, or lambda is 2q over pi r. Does that seem okay with you guys? Excellent. So bringing all the pieces together, I have dq equals 2q over pi r d theta. All righty. I have found a way to express dq in terms of the charge density and something related to the structure of my system, theta. I need to build my integral, and to do this so, I need to consider first dE points in the direction of r, but I have symmetrical contributions. So I believe, although I need to break this up into dE in the x direction and dE in the y direction, I believe dE in the x direction is the only one that matters, and that dE in the y direction will be 0. Right? There's enough symmetry that I can state that. Go ahead, Emily. I know that. So the mistake came here. When I subbed in for lambda, I forgot to put r d theta instead, and I just put just theta. And I do appreciate being corrected. I don't have an ego. You see what I do for a living, right? So no ego anymore. Just a peon public servant. So 2q over pi d theta. All right? Excellent. And peon has your grades in my hands, but what do you care? You're all seniors. So I need to, of course, do one more thing, and that is recognize that this expression would be for the entire, entire contribution to the electric field, but we only want the component that is along the x direction, which would be this direction. So I'm going to take dE and multiply by cosine theta as a means of getting the component of the electric field that I actually want to sum together. Good enough? I think I can assemble everything now. I don't have to worry about an expression for r here because every piece of charge is the same distance away. And so they're all going to be capital R based on the variable in the problem. So let's build my integral. dE in the x direction equals, and let's try not to screw this up too much, Eric, k dq, which is 2q dq, all divided by, looks like pi r squared. I think that's it. Oh, cosine theta. So I got my 2q over pi, I got my d theta, I got the r squared, I got k. I think that's everything. So now I need to decide how it is that I'm going to integrate this. But just getting to the next part, putting the integral sign on both of them and determining my limits, this probably gets you almost all of the credit. Probably 1 point for doing the calculus, but you're not going to get a lot. We've talked about this a little bit in the past. So let me just kind of throw it out there again. Whenever you have something symmetrical like this, you can run into an issue with trig functions and integration. So if you can, try and break it up in such a way that you aren't going from the same negative and positive direct angle. So I'm going to break this up and say that I'm going to start at 0 and go out whatever that's going to be, 1/8 of a circle. So that's 45 degrees. What is that? Pi over 4. Is that right? That's good to know. So I'm going to multiply by 2. I'm going to have the integral from 0 to pi over 4. And I could have just gone because somebody's going to ask in like 10 minutes. So let me just talk with my slow voice and say I could choose to go from negative pi over 4 to positive pi over 4, but that brings its own problems in the future from time to time. And since I know it's symmetrical, I'm introducing a 2. So the first person to ask where the 2 came from, I know now I get to like slow down and be shockingly condescending because I'm explaining it for the third time that I'm going to multiply by 2 and only integrate half of it. Triple dog dare you, Owen. I don't think Owen would ask though, he knows. There we go. Stop egging him on. Almost all of those are constants, right? Almost, oh, I put a theta, but that's a q. So there, q. So everything comes out except for the cosine, and you're just integrating cosine. So I think we've done all the heavy lifting here. Do we need to complete the math, or are we good? I think we're good, right? I want to stop here. So you can do math. Math is pretty easy. But, I mean, the heavy lifting is getting to this point. And I am sure that they're only going to give you a couple pieces of points here, but I bet finding some way to express this ends up being a point somehow in there. Probably coming up with your way that you're going to integrate ends up coming, probably ends up being a point. Usefulness of Coulomb's law might be a point. I mean, these are the ways they're going to get the points there. And probably something about setting up and executing your calculus will be a point. Remember, the current exam is really more about the physics portion and has really devalued the mathematics portion. And truthfully, back then, like I said, this was from 1977. So, but we've seen the ring problem, maybe 6 times throughout the course of the year. There are lots of examples of the ring problem. The features I think it really just wants, I think you have to have the 0 here for the point. I think you have to have the decay here to get the point. And I think you have to have it clearly showing a peak. If you knew the shape of the curve going up to that peak, or it's very clear, because I didn't derive it real quick, but it's very clear, like we know with some of the spherical ones, that it's linear, you better make that linear. But this one does not have an abrupt change because we're not just reaching the limit or the edge of being inside a charge distribution where there's a abrupt change in the charge distribution. This should produce a smooth curve from 0 to a decay at infinity. Yeah. They don't give equipotential problems like this very often, but when they do, this is the most detailed one we've ever had. I mean, if you look at all the literature, there's never been one as detailed and scale intensive as this one. So, and there's stuff on here that that they talk about in the problem that is not necessarily easy to see here. So, a few things I think you can kind of figure out, like Q1's got to be negative, just from looking at the equipotentials. Can you guys see that? The electric potential gets more and more negative as we get closer to it. It's making a negative dip in the whole electric field spectrum there. Q2 is stated as being positive, but we could get that from the equipotentials, being that they're getting more and more positive as we get closer to Q2. So those two things are kind of known just from looking at the map. I also get from looking at the map that Q1 must be probably more negative than Q2 is positive, right? You see the equipotentials become way negative and go further negative as we get closer to Q1, where Q2, they don't get all the same distance positive. And also just look at the circles. Do you notice how the equipotential circles are bigger around Q1 than Q2? That's kind of telling you that it's making a bigger depression in the space around it, right? It's making a bigger impact, a bigger influence. So I'm thinking Q1 must be greater than Q2. Those are the only, there's takeaways, but I also do want to kind of scream to all of you, they gave us scale too. The only reason they would give us scale is they're probably going to have us calculate some stuff relative to change in potential with respect to position, and that tells me that we're probably finding the electric field somewhere. There's no reason to give us that distance otherwise. Well, maybe there's another reason. So calculate Q1. They don't mess around, do they? So 2 charges, Q1 and Q2, are fixed in place on the x-axis at positions x1 equals -1 meters and x2 equals positive plus 5 meters. Charge Q2 has a value of positive 2.0 nanocoulombs. Values of electric potential are illustrated by the given equipotentials in the diagram shown above, which is drawn to scale. In order to find the charge, in my head I'm thinking, well, where's charge located in an expression related to an electric potential map? Well, it's located in the definition of electric potential. And these clearly look like point charges, and they kind of tell me they're point charges. So K, Q over R is our electric potential. It's clearly related to how far away we are from the charge. So there's two charges here. I could pick any equipotential line that I wanted to do this, because the equipotential from charge 1 plus the equipotential from charge 2 has to equal whatever the total equipotential is. So I would probably choose a line that I clearly know where it is between the two charges. And I'd also, if I want to make it easier, I'd look for 0, because 0 would be the right one to kind of do. That means they're both the same amount. And I'm looking, I see the 0 here. I would have to kind of figure out where is 0 on my map there. And that's what I would do to start out to find the charge.